Hi everyone, it's Elizabeth here. As Pamela explained, we're using the results of our survey to review common epidemiology study designs and measures of association that we learned about in class. In this session, we're going to look at the relationship between tea and coffee consumption at night and the risk of sleep difficulties. We'll consider which study designs can be used to address this question, what measure of association is appropriate, and whether there's evidence of confounding and effect modification by sex and age. We'll also give you an opportunity to conduct a similar analysis on your own using other variables in our survey dataset. Now, as we discussed in class, in order to make causal inferences about the effect of an exposure on an outcome, it's preferable when we have data where we can be sure that the exposure came before the outcome. In one of our surveys, we asked you about tea and coffee consumption in the 2 hours before going to bed and your sleep quality that night. But even though these questions were asked at the same time, they're asking about how tea and coffee consumption subsequently affected your sleep. So exposure occurs prior to outcome. Therefore, we can consider this to be a cohort study, where we first collect data on exposure to tea and coffee at night, and then we follow the participants forward in time to see who develops the sleep difficulties. The next question is, what is the appropriate measure of association? In a cohort study, we can use data on the number of exposed and unexposed cases and non-cases to calculate a risk ratio, or we can collect information about exposed and unexposed person time in our cases and non-cases and calculate a rate ratio. As you may recall from way back in the beginning of the course, we use rates when we're concerned about competing risk and loss to follow-up, when we have studies where people are followed for many, many years, and we're worried about not being able to observe all of the outcomes because of these issues of competing risk and loss to follow-up. But in the study that we're thinking about right now, we have information on tea and coffee consumption and their sleep quality that night, so we're not concerned about competing risks and loss to follow-up. Also, we often use rates when we want to understand the timing of how long it takes for the exposure to result in an outcome. But here we're not asking how long does it take for the tea and coffee consumption to cause a change in sleep difficulties. We just want to know, do they have sleep difficulties? Yes or no, case or no case. Therefore, the appropriate measure of association here would be a risk ratio. Our exposure variable is going to be CAF 2 hour before, which equals 1 if the person said that he or she did drink tea or coffee within 2 hours of going to bed, and equals 0 if he or she did not report drinking tea or coffee in the 2 hours before bed. And the variable equals missing if the person did not answer the question. Our outcome variable is sleep diff, which equals 1 if the participant reported sleep difficulties that night, and 0 if the person did not report sleep difficulties. For those who do not answer this question, the variable has a value of missing. Now, since our previous demonstrations have shown you how to calculate risk ratios in Stata, I'm just going to review the output for these analyses, but you can refer to our handout for complete instructions on how to use the Stata drop-down menus or the command window to obtain the results that I'll be showing you here. So here are the results from the CS, the cohort study command in Stata, looking at this relationship. Now the columns show people who drink tea or coffee 2 hours before going to bed, the exposed individuals, and the people who did not drink tea or coffee before going to bed, the unexposed individuals. The rows show the number of people who reported sleep difficulties, the cases, and the number of people who did not report sleep difficulties, the non-cases. And what we can see here is that among the 100 people reporting sleep difficulties, 19 reported drinking tea or coffee in the 2 hours before going to bed. And among the 491 non-cases, 102 reported drinking tea or coffee before going to bed. Our risk ratio was 0.91 with a 95% confidence interval ranging from 0.58 to 1.44. This means that those who drank tea or coffee before bed had 0.91 times the risk of sleep difficulties compared to those who did not drink tea or coffee. And we're 95% confident that the true value for this risk ratio ranges from 42% lower risk of sleep difficulties to a 44% higher risk of sleep difficulties. Now, although we would have thought that tea or coffee would actually increase the risk of sleep difficulties, that's not what we observed in our data. Maybe it wasn't caffeinated tea and coffee. Maybe they were drinking chamomile tea, so it was relaxing. It's also possible that there's some third factor related to both coffee and tea consumption and also related to sleep difficulties. So we'll want to consider issues of confounding. Another consideration is whether there's a weak association here overall, but that among subgroups there is a strong association between tea and coffee consumption and sleep difficulties. So we'll want to consider the possibility of effect modification. So let's explore whether confounding or effect modification may help explain why we observed a different result than what we expected. A common variable that people consider a potential confounder or effect modifier in many studies is sex. So let's run an analysis adjusted for sex to see if confounding by sex is occurring, and we can also use this same output to see if there's effect modification by sex. Now, we can use the same data code as before, only now we're stratifying by sex. And in our data set, we're using a variable called male, which equals 1 if the survey respondent is male and 0 if the respondent is female. We used formats to make it easier to interpret your results. So this will show in the output as a yes if the person was male and no if the person was female. And in the center of this table, we can see that the crude and Mantel-Hansel adjusted risk ratios are quite similar. The crude risk ratio is 0.911, while the Mantel-Hansel adjusted risk ratio is 0.914. And since the crude and adjusted risk ratios are so similar, we conclude that there's no strong confounding by sex in our study. Our output also shows us the risk ratio among females and among males. The risk ratio among females was 0.67, whereas the risk ratio among males was 1.24. And we can use these stratum-specific risk ratios to determine if there's effect modification by sex. Now, although our risk ratios do seem quite different from each other, when we do a test of homogeneity, we have a p-value of 0.1895. And since this value is greater than 0.05, we conclude that there is no statistical evidence for effect modification by sex. As we've discussed in some of the lectures, sometimes the point estimate suggests that the association between two factors is different between two subgroups, but we just don't have the statistical power to identify this as effect modification using our test of homogeneity. Now let's consider confounding and effect modification by categories of age. In order to maintain the anonymity of the survey respondents, we created a variable called AgeCat for you. And as you can see from the codebook, which is included at the end of this data demo handout, AgeCat equals 1 for respondents 18 to 29 years old, it equals 2 for respondents 30 to 39 years old, it equals 3 for respondents 40 to 49 years old, and it equals 4 for respondents 50 years of age and older. And in the center of the table, we see that the crude and Mantel-Hansel adjusted risk ratios are quite similar. The crude risk ratio is 0.911, and the Mantel-Hansel adjusted risk ratio is 0.914. And since the crude and adjusted risk ratios are so similar, we can conclude that there is no strong confounding by age category in our study. Our output also shows us the risk ratio for each age stratum. For example, the risk ratio was 1.2 among those 18 to 29 years old, but the risk ratio was 0.51 for those 30 to 39 years old. But despite these differences in the risk ratio among the different age strata, our test for homogeneity has a p-value of 0.4957, suggesting that there is no evidence of statistically significant effect modification by age category. Now that we've reviewed this example, you can practice a similar exercise using the Stata dataset for the survey data. Construct your own analysis to study the association between handedness and sleep difficulties. Consider confounding and effect modification by age. The syntax and results for this analysis are included in the handout. Have fun!